Hello, this is a talk for the ICCV 2021 workshop on 3D object detection from images. Welcome. Artificial intelligence and robotics have made great progress since the 1950s, but AI systems mostly work really well in simulation these days, and robots often still struggle with the real world, as in this example here at the DARPA Robotics Challenge, in the case of manipulation task. But this is also true, for example, in the case of self-driving, where expectations have been consistently high, but we still lack robust self-driving vehicles at scale on the road today. Why is that? Well, I believe that one fundamental missing component is robust perception. And while perception in computer vision has developed originally by the needs of the robotics community, due to its size, it has developed into its own community. And that's true not only for computer vision, but also for other fields such as computer graphics. However, I believe that in order to make progress towards full autonomy, it's important to make a concerted effort to not forget about the downstream application, but to, in a concerted way, advance both the perception as well as the action side. And an important element here is also computer graphics these days, because a lot of these systems we have to train and to validate in simulation as well, because we just can't afford to do all of this in the real world. While these communities have grown into their own fields and became really big these days, there recently has been some interest in reconciling them. And I want to show you two works here briefly from Fladl and Colton's lab that work at the intersection of perception and action. This one here, Does Computer Vision Matter for Action, looks at how important are the intermediate representations that computer vision can generate in order to conduct a downstream task such as driving. And it turns out they are relevant, and it's important how we choose them. So it's important to take into account the downstream task when making decisions for how to design perception modules. Similarly, simulation, I believe, will play an increasingly important role, because we are just not able to drive all these miles in the real world that are needed to reach the safety level of a human driver. So we need to train, to test, and to validate in simulations that are realistic replicas of the real world. This is the theme of this talk. I believe that towards full autonomy, we must exercise a concerted effort across multiple different fields that have grown into their own major research areas these days. In particular, these are computer vision, computer graphics, and robotics, and of course also machine learning, which is a fundamental, which provides fundamental concepts for all of these three. But the question, of course, is which data sets and benchmarks do we need? Is, for example, the KITTI dataset that we have introduced almost 10 years ago now, is that enough? And in this talk, I want to argue, no, it is not. And that's why we propose a new dataset called KITTI-360 that has a larger field of view, more sensors, and also more annotations. And with new benchmarks that will also provide to the community, we hope we can make better progress towards the end goal of full autonomy. Here's an overview of the KITTI-360 vehicle and data. On the top left, you can see the KITTI-360 vehicle, which is similar to the KITTI vehicle, but which comes with two additional sensors: fisheye cameras for 360-degree surround view and a SICK mushroom laser scanner for more complete 3D point clouds. You can see the point clouds from the different modalities calculated here in different colors on the top. And you can see two examples of the fisheye images here on the right. In addition to this rich 360-degree sensor information, the KITTI-360 dataset also provides semantic and instance labels in both 2D and 3D, which are consistent both in space and time. So you can use that dataset in both in 2D and in 3D, and also in 2D and 3D. In addition, we have better and more accurate global localization in this dataset, and we provide a series of new challenging benchmarks with a website where, as in the KITTI dataset, you can upload your results and get ranked on a public leaderboard for which the ground truth is held out. The data has been collected also, like in the KITTI dataset, in the neighborhood of Karlsruhe in Germany. But as you can see from this map, the trajectories are largely disjunct with the trajectories from the original KITTI dataset here in blue. In blue are the original KITTI dataset trajectories, and in red are the trajectories from the KITTI-360 dataset. In addition, we provide now geo-registered poses by fusing visual features, IMU measurements, and GPS measurements all together into a globally coherent pose estimate, which allows you now to utilize information such as OpenStreetMap or mapillary metadata in your projects. The sensors are 2 perspective cameras to the front, 2 fisheye cameras to the side, a Velodyne 64 beam LiDAR laser scanner, and a SICK pushbroom LiDAR, and of course an IMU GPS measurement unit. One crucial problem we faced when creating this dataset, and we started already 5 years ago, so this is now finally the release 5 years after we have started this effort, is how can we actually annotate semantics at large scale? And this is where the curse of dataset annotation comes in. This is a slide that I've already presented 5 years ago. So what you can see here on the x-axis is the annotation time for a particular modality, and on the y-axis the number of images a dataset provides. And you can see that, for example, in the case of image classification, we can annotate a lot of images, because annotating each individual image is relatively cheap. However, if you go to 2D detection or 3D detection, because annotating now the objects in the images is more expensive, we cannot afford as much time anymore. So we have less images annotated. And if you go to semantic segmentation or instance segmentation, it becomes even worse, because now you have to outline the contours of each of the objects. And this takes more time. And so, for example, the Cambit or the Cityscapes dataset provides significantly less data than the ImageNet dataset. So it's hard to overcome this barrier. And that's one of the things that we wanted to do with this dataset, to have a data point here where we have very accurate semantic and instance segmentations both in 3D and in 2D, but we have also a lot of images annotated, and we have everything consistent. And the way we do this is with the idea of 3D to 2D semantic and instance labeled transfer. What we do is we don't annotate images. We annotate 3D scenes in 3D with 3D bounding primitives, such as spheres, as you can see here in the case of trees, or 3D bounding boxes for buildings or cars, or 3D polygons for roads and sidewalks, etc. And then the idea is to take this information and project it back into the images in order to obtain also semantic and instance information in the images that's consistent both in space and time and consistent with the 3D annotations. The advantages over 2D annotation are that, well, object instances can be more easily separated in 3D. Think about trees or cars, which have a complicated structure when projected into the image domain, but which are easier to separate in 3D space. Furthermore, a single annotated 3D object projects into many frames. For example, if we look at a car, we see that car maybe already 50 meters ahead, and then once we come closer, we see it in every single frame. So it wouldn't make any sense to annotate that car in the image space, because we would do the same effort multiple times. We want to just do it once. We want to annotate in 3D space and then project the annotations back into the images. Another advantage of annotating in 3D is that the 2D annotations automatically become temporally coherent, because we're annotating the same object only once in 3D space and projecting it into many views, so we have the same instance label in all of the images automatically for free. And then of course 3D annotations are useful by themselves, as evidenced here by this workshop also on 3D object detection. But there's a lot of challenges with this process. First of all, outer 3D data that comes from LiDAR scanners is sparse, noisy, and incomplete. And the 3D annotations are coarse and imprecise often, because we don't want the annotators to spend a lot of time with the 3D annotation tool, which is also quite involved in getting used to. And so they should just do it quickly enough so that we actually also get the time savings that we want. And then, of course, annotating dynamic objects is challenging, because we have to annotate them over multiple frames. We have to track them. This is what the data annotation tool looks like, and we'll provide that tool also for free as open source to the community. So if you have a data set that you want to annotate that comprises accurate localization, calibration, and multiple sensors, you might find this tool beneficial for yourself. It's a web-based annotation tool, so it runs in the browser, can be used by people across the world. It has a 3D view and multiple 2D views, and it visualizes the cameras, and you can switch forward and backward. It has different controllers for controlling the view, but also the semantic annotation panel here at the top. And by using these annotations, this idea of annotating in 3D, annotating things only once, we require about 1 minute only for annotating a single image, because we're annotating many images at once by back projection. In comparison, for example, to annotating the cityscapes dataset, where each image had to be annotated independently and required about 60 to 90 minutes. This is a little example of how this annotation tool looks like. You can see the images here on the top, and then the 3D viewer here at the bottom. Here's an example of static object annotation. In this case, we want to annotate this car. We drag a 3D box, we initiate a 3D box, and then we refine the 3D box based on a crop. We can change the visualization to help the annotator to better select the 3D box. And this is an example of annotating dynamic objects. First of all, dynamic objects need to be spotted. And then the key of this tool is that it allows you to annotate only a few keyframes, and then automatically tracks the objects in between, and you can refine the annotations. And so you don't have to annotate each frame individually, but you get results pretty quickly. Now, having annotated all the 3D point clouds that we have accumulated from our 3D sensors, we want to project this semantic and instance information into the 2D image domain. And we do this using a densely connected CRF, conditional random field model, that connects densely all 3D points with respect to each other, all 2D pixels with respect to each other, and all corresponding 3D points and 2D pixels. And it comprises multiple terms. I'm not going to go over each of these terms in detail, but what I will tell you is that, well, of course, the 3D points and the 2D pixels are influenced by the labels, by the 3D bounding boxes that we have, the annotators have annotated, have labeled in the 3D scene. And then there's some additional inductive biases that we make use of, such as smoothness biases or biases of deep neural networks for image segmentation that we train on the fly through sparse but very confident back-projected 3D points, and that help us in the process of establishing unary information. Inference is then conducted by a factorized mean field method, similar to this seminal work from Graham, Buell, and Coulter in CVPR 2011. And an advantage of this modeling paradigm that we're using is that it allows us to also estimate confidence per pixel. Remember that the 3D annotations are not always accurate, so it's useful to know the uncertainties in our annotation procedure, in our inference procedure, in order to use less of that information for training algorithms or for evaluating algorithms. And we do this by computing the entropy over the marginal distributions that this algorithm returns. And it turns out that these are quite well calibrated, as we will see in a second. Learning happens, there's some parameters in this model, so learning of these parameters happens through empirical risk minimization with SGD. And the one other nice advantage of our model is that we can treat semantic and instance segmentation exactly with the same model. It's just a different label set for us. Here are some qualitative results. This is a result of a 2D label propagation baseline that, using techniques such as optical flow, tries to transfer 2D segmentation annotations from one frame to another frame. And this doesn't work so well, in particular if the optical flow is not very precise. And here in contrast, you see the results of our annotation technique. You can see that here in color, some of the labels are still incorrectly estimated. But what's nice about this method is that at least we know roughly when pixels are inferred with uncertainty. And this is illustrated here. This is an ablation study where, first of all, you can see that each of the components in our model helps a little bit, but also that if we drop out pixels from the evaluation, and this is evaluated against 2D human annotated, 2D semantic segmentation ground truth. So if we drop pixels based on the uncertainty that we infer, the accuracy and the Jakar index dramatically increase. For example, if we use only 70% of the pixels that we have inferred, then we get a 97.5% Jakar index and 98.7% accuracy. And this is also visualized here. You can see the inference results, the boundaries in the first two images here that have been inferred also for dynamic objects, and then the semantic segmentation results in the middle row, and the uncertainties at the bottom, where you can see that in the regions where the method does some mistakes, also because the 3D point clouds are noisy, etc., at least we know roughly where the mistakes are happening. One nice thing about this procedure is that, of course, we also obtain semantic and instance segmentation results in 3D. And here are some examples of that. These are semantic segmentation results, and these are the corresponding instance segmentation results. Semantic segmentation, instance segmentation. Semantic segmentation, instance segmentation. Now, once we have this data set, of course, we have to ask ourselves, how can this data set help in autonomous driving? Can we define, using this new data set, novel benchmarks that might foster progress in research areas that are relevant towards full autonomy? And while this is still preliminary, and we plan to extend this in the future, as we also continuously extended the KITTI dataset, we've started with a set of initial benchmarks that we think are important to make progress. And these benchmarks are situated at around or in between computer vision, graphics, and robotics. In particular, we have semantic scene understanding benchmarks, we have novel view and semantic synthesis benchmarks, and we have a semantic SLAM benchmark in our current portfolio. Semantic scene understanding benchmarks comprise 2D and 3D semantic and instance segmentation, 3D bounding box detection, and semantic scene completion, where only a partial view is provided, and both the geometry and the semantics have to be completed by the algorithm. Here's some examples of how this data looks like. This is for the semantic segmentation and completion benchmark. This is for the instance segmentation benchmark. And this is for the 3D bounding box detection benchmark, where you can see both buildings and vehicles with their corresponding 3D bounding box labels. At the intersection of computer vision and computer graphics, and towards photorealistic simulators and replicas of the real world, the KITTI-360 benchmark provides tasks for novel view synthesis, both in terms of appearance synthesis and semantic synthesis. Here in this case, the input is a set of perspective and fisheye images at sparsely sampled viewpoints, and optionally also the 3D point cloud, as well as the poses of the cameras. And the output that we evaluate is the RGB image and the semantic map, semantic label map for novel viewpoints. In other words, we are measuring how well a particular method was able to synthesize, how photorealistic it was able to synthesize a novel view image, as well as also the semantic label map that corresponds to that image. And finally, at the intersection of computer vision and robotics, we've defined a series of Semantic SLAM benchmarks. The first is just a simple localization benchmark, and then Semantic SLAM requires the methods to both estimate the trajectory of the vehicle, but then also infer the geometry and the scene semantics, as illustrated here on the right. This is the ground truth from one of the sequences of the benchmark. For all of these benchmarks, we provide, as in the original KITTI dataset, a leaderboard where people can submit their results and get ranked on the public leaderboard. Finally, here are some resources that we provide. The first link is to the KITTI-360 dataset. Then we provide all the utilities and scripts to get acquainted with the dataset and to use the dataset and work with the benchmarks. We have an annotation tool available also in terms of source code, and a little video, which I want to show you parts of now. Also, this is the teaser video for the KITTI-360 dataset, where you can see what one particular scene, we have many of those, looks like in terms of its 3D point cloud, in terms of the semantic segmentation and the instance segmentation, as well as the sensor modalities. That's all from my side. Thank you very much for your attention. We hope really this dataset will become useful to the community in the future. And we're looking forward to seeing your results on this dataset.